Hello everyone. Today I'm going to introduce our research paper, OA Mine, Open World Attribute Mining for E-commerce Products with Weak Supervision. This is a collaboration project done by Xinyang and Jiawei from UIUC, Chenwei and Xian from Amazon, Luna from Meta, Qingbo from UCSD, and Crystals from CMU. My name is Xinyang, and I will be presenting today. First, let's talk about what is product attribute mining. So given an e-commerce product, for example, the TV product here, product attribute mining aims to extract the attributes from the product. For example, resolution is an attribute of a TV, and also the values for those attributes. For example, 4K UHD is a specific value for that attribute. Traditionally, product attribute mining is done with a closed-world assumption on the attributes, which means you have to specify the set of attributes you want to extract. So for example, you can tell, okay, I want to extract brand and color and maybe also item form. And then you can annotate your data and build your model. So typically that model is going to be a named entity recognition model, which is usually a sequence tagging model. And then you can train your model using your data and run the model through your text. But here in this project, we're doing a more challenging problem with a fully open world assumption, where we want the model to find both new attributes and new values. So you may ask why we want to do this open world setting. And the most important reason is that in the e-commerce world, the product catalog is forever expanding. So for existing types of products, they may get new attributes. So for example, when you are shopping for a TV 10 years ago, HDR compatibility is not something you consider, but it's very important nowadays. And what's more, we may get new types of products, these days. For example, VR headsets is not a thing 10 years ago, and now people are shopping for that. In this challenging problem setting, it is very expensive or may not even be feasible to build a fully supervised model because of the forever expanding product catalog. You cannot really keep up your annotation with that data. So here in this project, we focus on a weak supervision setting. And our supervision is going to be seed examples. So we give the model a few known attribute values for each known product type. For example, we may tell the model for tea products, we have an attribute with value loose leaf and tea bag. And we have another attribute with green tea and black tea. And for coffee products, we may tell the model, okay, we have whole bean and K-cup, that's one attribute. And we have dark roast and light roast from another attribute. To wrap up our problem setting, for the input to this problem, we have product data, which includes product text and also product type. We also have weak supervision as input, which we have just introduced. We have seed attribute values as weak supervision. For the output, we want the model to find both new attribute types and new attribute values. So the output is going to look something like this. For each product type, the model will output a bunch of clusters, where each cluster represents an attribute of that product type, and each member of the cluster represents an attribute value of that attribute. So looking at the example here, for those attributes with seed value, for example, the item form and type of tea products, we want the model to find more values for those attributes. And what's more, we want the model to be able to discover new attributes. For example, we want the model to discover flavors of coffee products. Working on this new problem, we collected our own data, and we open source that data. And we also designed a framework which is very different from those NER-based framework designed for product attribute mining. We have our focus on an attribute-aware representation learning process. There's no open source data set for this problem, so we collected our own data. We collected around 80,000 Amazon products from 100 product types. So those products, they come with text and also some attribute information, although they're not perfect or complete. Otherwise, we don't have to do this project. And we use those available attribute information to build the dev set for evaluation. And more importantly, we also built a test set with human annotation. We selected around 2,000 products from 10 product types. And we hired crowd workers to annotate them. and we then consolidated our label by hiring expert knowledge associates. Before we jump into our method, I want to highlight 3 observations from the data. The first observation is called title first, which means the most important attributes of a product will be in the product title. And that's because the seller want to maximize the exposure of their products. The second observation is called bag of values. So if you look at the product titles, they are not really spoken language. They are usually just a collection of attribute values. The third observation is called value exclusiveness, which means the attribute values in the product title usually don't repeat themselves. So for example, for this TV product, if the first part of the product title is the brand, then the rest part of the title will likely not repeat this brand. These observations will motivate the design of our framework. And based on these observations, in this project, we work on product title text only. We do not work on other textual content of the products. Here's an overview of our framework. There are 2 steps in our framework. In the first step, we take the product text, also types, and we generate a set of candidate attribute values from the raw text. In our second step, we take those candidate attribute values, as well as our weak supervision, and we group those candidate values into clusters of attributes. And our second step is an iterative process. Now, the first step, attribute value candidate generation. In our first step, our goal is to obtain candidate attribute values from products with high recall. So for example, our input might be a coffee product, and for the output, we want to segment this coffee product title into candidate attribute values such as Green Mountain Coffee Roasters, Caramel Vanilla Cream, stuff like that. The way we're doing it is we probe a pre-trained language model. The overall idea is a pre-trained language model should capture the word-to-word impact in a sentence. And our steps, the first step, we do language model fine-tuning on our in-domain corpus. The second step, we build a word-to-word impact matrix. In the third step, we chunk out the attribute candidates based on the scores in the matrix. From the impact matrix, we can derive the pairwise score for each pair of adjacent words, and we can segment the whole product title based on those scores and a predefined threshold. We compare our method to NLP non-phrase chunking tools such as Spacey and Flare NLP, and also to phrase mining tools such as Autophrase and UCPhrase. You can see that we have a pretty decent performance gain across the board, and mostly this is because those NLP tools they are not trained for product titles. And while our method is fully unsupervised in this step and uses a pre-trained language model. Now comes our second step, attribute value grouping. For this step, we have already got a set of candidate attribute values. Our goal is to group these candidate attribute values into clusters of attributes. And here, we're also using our weak supervision as guidance. Our overall idea here is to run clustering on the value candidates generated from our first step. But here there are several challenges. First and foremost, a pre-trained BERT is not attribute aware. Secondly, we want the model to generalize to new attributes and product types, which means for those attributes without any human-given seed values, we also have to solve it for that part. And thirdly, we also have to take care of the noise from the candidate generation step because we cannot assume the first step of our framework is perfect. Let me show you a little bit more why a BERT model plus clustering does not solve the problem. Here we show visualization of embeddings of value candidates generated from the first step. They are colored by the ground truth attribute type. On the left, we can see that with BERT for embedding, attributes, values from the same attribute type are not always close to each other. And what we want is something like the one on the right, where we want the embedding to capture attribute type information. To make it happen, we designed this attribute-aware fine-tuning framework. For input, we have value candidates from our first step, and we also have the weak supervision as seed attribute value sets. We use multitask objectives to fine-tune a BERT model. The first task is a binary meta-classification task, where we give the model a pair of value candidates and let the model tell if they are from the same attribute or not. We call it meta-classification because this is not designed for a single attribute. Rather than that, we want it to generalize to every attribute and for every product types. The second objective is a contrastive learning objective, where we want the model to have a smaller distance for values from the same attribute and have a larger distance for values from different attributes. The third objective is a multi-class classification objective, where we give the model a value candidate and also a product type. We let the model put the value into the correct attribute. So this multi-class classification objective will enforce the exclusiveness of attributes. All of our value candidates will be fed into a shared BERT encoder, and the multitask objectives will be optimized in an alternating way. For the shared encoder, we use a BERT model plus entity pooling. So we give the full sentence to the BERT model, and we only take the representation for that specific value candidate. And here are our specific objectives for each task. After we have fine-tuned the BERT model and made it attribute-aware, we can then apply that model to obtain embedding for all the value candidates. On top of that, we can apply a clustering method to generate the attribute clusters. But here, we cannot just apply any clustering method. Recall that, first of all, we have to discover new attributes. And secondly, we also have to handle the noise from our previous candidate generation step. So here, the clustering method we use is dbScan, which is a density-based clustering method, and it can exactly solve those two problems. It does not require the number of cluster as input, and it can also handle noise. But one downside of dbScan is we find dbScan to be actually quite precision-focused in practice, which means it will put lots of useful stuff into the noise cluster. And to resolve that issue, we actually took the classifier from our fine-tuning step, and we applied the classifier on the noise cluster to pick useful stuff back from the noise cluster and put them into the correct attribute clusters. So the overall inference step is a self-ensemble, which combines different parts of our model. The representation fine-tuning and inference can be run in an iterative way. So after one iteration of the model, we have confident predictions, and then we can combine those confident predictions with the weak supervision we have and further fine-tune the representation and generate better attribute clusters. For the experiments, we don't really have a prior method on the same subject, so we compare it to all sorts of baselines. We have prior methods on product attribute mining here, so they are sequence tagging based and they are closed world. And we also have unsupervised clustering methods and another open world classification method that we adapted here called Deep Align Plus. For this task, the output are a bunch of clusters. So we use clustering-based evaluation metrics like ARI, Jacquard, NMI, and recall here for evaluation. From the results, I want to highlight a few points. Firstly, if you look at the sequence tagging-based method, they do not perform well with limited training data. And secondly, for BERT plus AG class, which is a method that does not handle noise and include everything in their prediction, it does have a better recall on the test set, but it has a very poor performance judged by other metrics. And overall, our method just performs better than the other methods across the board. Like we said, we want our method to be able to discover new attributes. So we run another set of experiments where we hold out 20% of the attributes with cross-validation. And here you can see quantitatively our method performs much better than the baselines. Another more challenging task is to evaluate the model to new prototypes without any supervision or seed information given. So the way we're doing this is we use 90 prototypes for training and evaluate on 10 new prototypes. And here you can also see we have a fair advantage over the baseline methods. In summary, we approached a new problem, open-world attribute mining with weak supervision. We collected our own data for end-to-end evaluation, and we designed a new method for this problem, which is a two-step framework with a special highlight on attribute-aware fine-tuning. That's our presentation. Thank you.